Our next speaker is Hemmati from Caltech IPEC.
Hello, everyone. My name is Shubi, and I'm a staff scientist here at IPEC. Today, I'm happy to talk about this project that I've recently been working on called JASP, stands for Joint AI Survey Processing. Those at IPEC might already be familiar with an earlier version, which was Joint Survey Processing, work that George Helou, Rangaram Chari, Andreas Feist et al. Were doing. So this one has an addition of myself and AI to it. And so I'll be talking about some results from Rubin, jointly processing Rubin and Euclid. But for the Roman enthusiasts in the room, every time I say Euclid, you hear Roman. Okay, so why do things jointly? Mostly because all the missions that I mentioned are cosmology missions, and cosmology is really limited by systematics and not statistics. So if we can push things to earlier rather than later, so pixels rather than catalogs, and combine things there, we have a better handle of systematics. So we can learn PSFs, we can know different resolutions, etc. And the idea of adding AI is really not to do a shortcut, but to learn from everything that classical efforts have been doing for decades and use those as benchmarks. And of course, the same kind of rigorous effort has to go into the AI works to get it to the level that classical works are at. Okay, so the data that so the data that went into this is very early on data of both Euclid and Rubin that are public. So Euclid is Euclid Q1 data, which is so here Euclid Q1 in Viz and in near-infrared YJH, so 4-band Euclid, and so these are already processed near-infrared imaging NISP that are transferred to the Viz pixel scale of 0.1 arcsecond per pixel. And for Rubin, this is pre-LSSD, so it's just data release 1 from the commissioning camp in 6 bands UGRIZY with 0.2 arcsecond per pixel. So we are going to combine these. And the idea is use the fields that are in common already published, and then we extend it to everywhere else that will have data from both. Here is where our training, testing, validation happens in ECDFS or Fornax field. It's 790 tiles, and this is one tract. If you speak Rubin language, this is one tract, 6 patches of a sky. It contains about 50,000 galaxies. And up there, we have another field very separate in the sky, and that is our out-of-distribution field. Basically, we do everything in the other field and then test whether if we use these models somewhere else in the sky, does it transfer well or not. And what the model sees are these 10 bands here. So UGRIZY from Rubin, and then Viz, YJ, and H from Euclid. And this is basically 512 pixels by 512 pixels in Rubin, and half of that in Euclid. So that's the data that goes in for training. Now, what's the idea of doing a foundation model? So we want to train one model once with these 10 bands, so learn these space of a spectral, spatial Euclid plus Rubin, and then use that learned representation to do all the other measurements on top of that. So the foundation gives us that representation, then we have measurements of different things which we call downstream tasks that we do after. For example, we can do astrometry, we can do detection, we can do shape measurement, anything that you're interested in, redshifts, etc. Here I'll talk about detection and astrometry if I have time, and then the rest are in preparation for force photometry, shapes, etc. Now, this foundation model, it's called foundation, but you shouldn't be scared. It's not like an LLM with hundreds of billions of parameters. It's a small one compared to those, so 9 million parameters only. It takes about 3 hours on a GPU to train. And so it's lightweight. Once trained, you can use it to do everything else on top of it. This is how the architecture looks like. So the two instruments go through their own different convolutional networks, these are conv-next, which is a very modern way of CNNs. It beats vision transformers. You don't care about those things. But then they go through their own stems. They get fused here together. So here you have a space that knows about Euclid and Rubin together. Then they go to some transformers, which learns about the relationship between different things in that space. And at the end, you use some decoder that tries to reconstruct one of the bands here. So the way that we train this is we have 10, we take one out, so we do 9, and then we try to reconstruct it at the end. So this is basically telling you that we are learning this space by being able to do the reconstruction at the end. What the downstream tasks see are the features that come out of here, so we don't care about the decoder after we have the foundation trained, and those frozen features then come to a smaller subnetworks that do different measurements, for example, detection head, astrometry head, etc. Okay, so this kind of architecture lets you do keep resolutions without doing resampling, so you don't have to put everything in the same resolution before combination, and you can do measurements at their native resolutions. When Roman is here, you can either replace Euclid with Roman or add another one on top of here. Now, this is my most interesting slide. If this was an AI conference, this would take about an hour to talk about. Here, I'll talk about it in 1 minute, hopefully, or less. But the idea is that kind of architecture doesn't come from the sky. You have to really play with all the different possibilities of put one piece of the Lego where so that it works at the end. And we tried many different things. One that I like, for example, JEPA. I don't know how many people have heard about that, but that's joint embedded prediction architecture. That's something Jan LeCun is pushing for in vision. And the idea there is you learn everything in a latent space, and instead of doing in the pixel space. Why it doesn't work for us? Because we care about things like astrometry. We care about where things are. We don't just care about what galaxies look like. So if you are interested in galaxy evolution, you can do something like JEPA. But if you want to do systematics, then you have to do everything in the pixel space. Okay. So this is showing you that the reconstruction works. Here I have truth in the first column, reconstruction by the decoder in the second, and residual in the third. And as you can see, the bands that were masked, we are able to reconstruct them. And of course, it's so the R value shows you how good we can do the reconstruction, and it's harder for Viz because Viz has the highest resolution. So if you take that out, it's harder to predict that from the other bands. But if you take one Rubin band out, you can reconstruct it easily from other Rubin bands plus Viz. And here it's showing you, this is a bit difficult to explain, but the idea is it's not enough if you can reconstruct with a decoder, because you still have all your model with the weights trained that give you that reconstruction. What you want is that feature that is frozen and coming to downstream tasks have idea about the space without the weights of the model. This is showing you that. It's basically telling you if I only use the features, do they know about the fluxes, or do they know about the signal to noise of blah, blah, blah galaxy in each band? And it's showing you that the R squared is quite high, whether you do it linearly or with some other MLP. And the subplot on the right is showing you which band does the model use in order to do the reconstruction. So the idea is AI is not a black box. If you know what is happening, you can basically see how much information comes from Viz, how much comes from NISP. You can see that the Viz bands here the NISP bands use mostly information from NISP, and they don't care what is in Rubin for the reconstruction. The Rubin bands use a bit of NISP also. So these are just validations of the foundation working. Here I'm showing you detection. So the model is trained well. The features go to the downstream head of detection. I tried two different detections. One is called CenterNet, the other STEM CenterNet. And the idea there is really to either to use only these frozen features or go a bit back and also bring the stems from here. And bringing the stems doesn't help too much, so StemNet is already good enough. It already finds everything that Euclid Q1 MER can find in images, and it also pushes, deeper than what is only possible with Viz. So here I'm showing you detection comparison with MER in the black line on top. And so detection works basically. And then we also checked astrometry, and here I'm showing you the circles. The outer circles are the offset when you don't use this foundation model, the offset compared to Viz, the offset of Rubin bands and NISP bands compared to Viz, and that's about 50 milliarc second. If you use this foundation model to correct for the position of objects and then remeasure offset, then you'll get to something like 7 milliarc second offset. Why is that helpful? So if you have very bright stars and you can measure the astrometry well enough, then you're good, unless the field doesn't have as many stars to do a good fit using those stars. So then you have to go and use fainter objects, which are harder to do astrometry on, and something like this foundation model can help you get a better fit. So here I'm showing you a fit of the astrometry offset with two different methods without using this foundation model, and the idea of using two is just to show you they give more or less the same kind of concordance field. And if you use the head and correct for astrometry, you can see that that field is gone. So we correct for astrometry to better than, I don't know, 4 milliarc second or so. So that's the idea there. Taking everything to the out of distribution field, so somewhere else on the sky works just as nicely, so you can use the model anywhere. And Roman is of course next. It can be Rubin Euclid plus Roman, or it can be Rubin plus Roman. Both works, and I leave you with my summary.
Do we have any questions?
Thanks. Great talk. So I just want to understand the third point. So are you saying that this is the disagreement between Euclid and Rubin, or between Euclid's like catalog and your recalculation from Euclid's catalog?
So thank you for asking the question, because I did the slide too fast. So both Euclid and Rubin are matched to Gaia. So for bright stars, they get to good astrometry. They get to something about 14, 15 milliarc second. But you don't get that kind of agreement if you go to fainter galaxies in the field, just because you can't center them well enough. Now, if you want to measure a field using only the stars, you can measure it well enough because you don't have as many anchors. With this, you can center the fainter things as well, so you remove even a small field in there. I don't know if I answered.
Okay, other questions?
It should be. Okay, so like, are you available to apply these same method to the probably like smaller ground-based telescopes, like let's say Palomar maybe, or GTF, and then like what would be like consequence like from there? I mean, do you think it will actually help the other way, like these like smaller telescopes as well?
Yeah, I think so. So I think, so you're saying Rubin isn't that bad. Why are you choosing Rubin?
Yeah, like you probably like an even worse case.
Yeah, I think it would be nice to try it on very poor resolution and see how much improvement you get there.
Other questions? Yeah. Jeff.
I was thinking about applications to more stellar fields than extragalactic fields. What does photometric variability or position changes, proper motions, do to this kind of analysis?
Good question, but not for me. Yeah, I don't know too much about that.
And then I had a quick question. Can you go to your slide where you looked at where you're pulling information from? So I think, in my naive opinion, I was surprised by this just a little bit because I'm always used to the bluer bands, just because of spectral feature information, right, being the source. But it seems like resolution, so it's pulling from YJH, right? It seems like that's the dominant factor. Is that the appropriate read to take from that slide, or can I have your thoughts?
So I have taken Viz out of this because if Viz is one of the bands in there, it dominates and you don't see the color from everything else. And because Viz has the highest resolution and it's Euclid, so it already knows about NISP because they are processed together. So that takes everything. But yeah, so if you do it per galaxy or per star, then you would probably see spectral features more there. But because this is a cutout that has many objects in it, you would expect resolution to play a more important role.
All right, let's thank our speaker once more, please.